Okay, let's continue our discussion on symmetries. We have learned about Lorentz transformations and other transformations which form a group. For example, unitary transformations, SUN or UN. Okay, so let me begin by a quick recap and some more words on what we have already talked about. So we learned about Lorentz transformations. Okay. So right now I'm not writing a transformation on the field. I'm just writing how they act on the space-time points which are denoted by x here. So you have lambda mu nu x nu here. Okay. And I was also mentioning about representations very briefly in one of the videos, meaning the elements of the group or the transformations, okay, in this case the lambdas, okay, they can have different representations, meaning you can find matrices which obey the same multiplication rule, okay, and they give a representation of Lorentz group or whatever group you are looking at. Okay. And in this course we have been very frequently looking at scalar fields. Okay, so let me say something about that. Okay, by scalar I meant always a field more clearly. So suppose instead of having one field like you had in Klein-Gordon theory, okay, suppose you have multiple scalar fields. So suppose you have a field phi 1, another field phi 2 and many more, and let's say we have total number n fields, okay, total n fields. And if they are all scalars, then I mean the following. I mean that if you do a Lorentz transformation, okay, then these objects phi 1, phi 2, phi n, they do not transform into each other. They do not mix among themselves. They only the transformation happens only on phi 1, only on phi 2 and so forth. Okay. Let me tell you what I mean here. So if your theory has all these fields, then let me write them as, collect them into a column. Okay. Then these fields will get transformed to phi tilde 1 x1 and up to phi tilde n x n, sorry, not x1, x, where the phi tildes are related to phi by the following. So of course you have to have here phi 1 lambda x, phi n lambda x. Okay, and as I said, there is no mixing that happens. So phi 1 goes to phi 1, meaning you have an identity, a unity in the diagonal. Okay, similarly here, so these are all zeros. So you have only diagonal entries. Okay, and the diagonal entries are the same. Okay, so that's the matrix which you have. So the representation matrix is identity, and your phi tilde is just phi tilde of x1. Phi tilde of x is just phi 1 of lambda x. Phi tilde n of x is phi n lambda x. So which means that the phi is not changing. The argument is of course changing, but that's besides the point. As far as the scalar term is concerned, it's just saying that the phi doesn't change into something else. Okay, so our representation matrices for lambdas, okay, if I am looking at scalar, then they are just Okay, and if you have only one field, like in real Klein-Gordon theory, then your d of lambda is just 1, just the number 1. Okay. There is another representation that we have already been writing, in fact, without even mentioning, and that is the representation formed by, just a second, representation. That's the vector representation which I am talking about now. So, when we wrote down the matrices, these ones, okay, these 4 cross 4 matrices, they form a representation, of course. They were used to define the representation. So, these 4 cross 4 matrices also form a representation, and there can be many more representations, but now we have at least seen 2 of them, one scalar and another the vector one. And you might already be aware of electromagnetic fields, and that you can write them as a 4 vector potential, which is a collection of these 4 fields. Okay. So, if you write down a theory with these fields, okay, A mu's, then the transformation law will be this. Okay. So, the components will mix. Now, earlier in the previous example where we were talking about scalars, A naught just became A naught, A1 just became A1. I mean, A1 remained A1, it didn't change. But here there is a mixing. So, A naught, A0 is lambda 0 nu A nu. So, you have a sum over nu. So, there is a mixing here, and the transformation is this. Okay. So, so here you can imagine, I mean, the way to understand this would be to imagine that you have these fields A mu's, okay, and you boost to another frame, or you boost them, okay. So, they become A prime mu, and these fields, this index nu transforms according to this rule, because this is a vector transformation you are looking at, okay. And then whatever was at, because now you are looking at a space time point x, and because you have done a boost, whatever was at lambda inverse x has been boosted to x, okay, or has been transformed to x. So, that is why you have lambda inverse x here. But what is more important to understand is that the fields are now mixing into each other. Okay. So, if the way we have been doing till now is that if you are given an action, okay, meaning if you are given a theory, you start searching for its symmetries. Okay, you are interested in knowing what symmetries it has, so you try to figure them out. But often you might be interested in doing the opposite. So, suppose you are constructing a theory of something, okay, and you have been told about what symmetries are there. Okay, so symmetries are known to you, not the theory, but some symmetries have been told to you, okay, and then you construct the action. Okay, but to do so, not only you should know the symmetries, which is meaning you should know the group. Okay, this means knowing the group. Okay, but let's say you have been told Lorentz group, you have the symmetry which is Lorentz symmetry, so you choose the Lorentz group, but that's not sufficient. You have to also decide on what fields you have to have in your theory, okay, which means you have to decide on the representation in which the fields transform. And then you are able to write down, then you can write down the action. So, you write down all possible terms that are consistent with that symmetry, okay, and once you have chosen your representation or representation, so you might have multiple fields transforming differently under different representations of the same group. and then you write down the action that is consistent with those symmetry and including all the representations. Okay, for example, here the representation was vector representation. So you could construct a theory which has scalar fields, let's say n number of them, or 1 if you wish, and you have and together with that you also have, let's say, a vector field in your problem. So you will try to write down a theory with these fields, okay, and construct an action which will be invariant under Lorentz transformations. So that is also often done when you are trying to make a theory. Okay, I have planned to give you one more example of a symmetry transformation. Okay, so let me do that. Okay. So here the transformation, right now I am not talking about the field, but I am just telling about what happens to space-time points. So take a space-time point x, okay, and let it get transformed to x prime, where x prime is related to x by a factor here, e to the alpha, where alpha is real. Okay, it's a real continuous parameter, so you can choose alpha, whatever real number you like it to be, and it can be varied continuously. Okay, this is called a scaling transformation, okay, or scale transformation. It's also called dilation. Okay, for example, if you take alpha to be log of 2, then your x prime is 2x. Okay, that is all your coordinates x1, x0, x1, x2 and x3, they are all being scaled up by a factor of 2. So that's why it's called scaling. Okay, you are just scaling it up, or you are dilating the coordinates. Okay, now you can readily see that the transformation, this transformation that forms a group. So you can check that it forms this scaling transformation, scale transformations form an abelian group. Okay, so they form a group. So all the 4 properties they will be satisfied that form a group, and also the order in which you do the transformation, that does not matter. So you can do transformation number 1 first, followed by 2, or the second one first and then the first one. So if I were to write e to the alpha times e to the beta, this is same as e to the beta times e to the alpha. Okay, so because these commute, we say that this is an abelian group. Okay. Now, if I am writing down a representation of this group, okay, then the matrices, remember the matrices D, let's call them D, and because they are parameterized by this parameter alpha, let me write it alpha, okay, they would be diagonal matrices. So it forms an abelian group, right? So if your group is an abelian group, then this has to be true, order should not matter. But now when you are looking at the representation, then the matrices have to commute because it's an abelian group. Okay, and matrices will commute if they are diagonal. Okay, so diagonal matrices they commute, so you expect the representation matrices to be diagonal. So now you can ask how will fields transform under this group. Okay, so imagine we have n number of fields, phi 1, phi 2, phi n. Okay, then under this transformation, under scaling transformation, they will go to something to phi 1 prime, phi 2 prime and phi n prime. Okay, and they have to be related by this kind of transformation. So you should have the representation matrix here and the fields here. So the phi 1, phi n, okay. And what will be this matrix? It will be diagonal, as we said, and we can choose the diagonal elements, all of them, to be this. So I write e to the alpha, that's the parameter which parameterizes the transformation matrix, but I keep a number d1 here. Okay, so d1 is a number here, and of course these are all zeros, and 0, d2, and so forth, dn. Okay. So these d1, d2, d3, they will depend on what kind of fields these are. Okay, I'll give you one example, and it will be clear that these will in general be different, and they will depend on what fields you have in the problem. Okay, but this is clear that it has to have this structure. So let me write down a theory which has a scaling symmetry, and this is already known to you. So let's look at the action of real Klein-Gordon theory. Actually, I will take massless Klein-Gordon theory. Okay. Let me emphasize, I am looking at massless Klein-Gordon theory. Okay. Now we consider the transformation phi tilde e to the alpha x. So that's what happens to x, but the field itself changes because we have seen what the representations are, right? We know that phi 1 prime is e to the alpha d1 phi 1. So here I write e to the alpha d1. In fact, I will determine what d1 would be. So I hope this is not appearing difficult. This is just like this situation here, this one. For example, a prime 0 is lambda 0 0 a 0 plus lambda 0 1 a 1 and so forth. Okay. So this matrix was your 4 cross 4 matrix, but here it was mixing all the components. In this case it is simpler, it does not mix phi 1 with phi 2, but there is an overall thing, okay, here, just like you had in this case. Okay, so let's do this simple exercise and check whether this is a symmetry of this transformation is symmetry. So let's calculate as before what is S phi of tilde. Okay. So you just write d4x half del mu, instead of phi we put phi tilde of x, del mu phi tilde of x. Okay, that's good. And then it becomes the following. So phi tilde is I substitute this one, so I get e to the 2 alpha d1 because there are 2 phi tildes here. So I get e to the 2 alpha d1, and this is because of phi tilde. Okay. Then you have this argument changes, so you get half del mu phi of e to the alpha x del mu phi e to the alpha x, okay, and integral d4x. Now as before, we will change the variables. We will write x prime as e to the alpha x, okay. So we can immediately write that d4x prime, which is same as dx prime 0, dx prime 1, dx prime 3. This is e to the 4 alpha d 4x. Okay, each of this brings a factor of e to the alpha. So d4x is e to the minus 4 alpha d4x prime. So now that I am changing variables, I write this one as d4x prime, this one e to the minus 4 alpha. Okay, then we have e to the 2 alpha d1, and these will become phi of x prime, right? Now I should change the derivative piece. Okay, and that's easy. So here let me write, so remember that it's del over del x prime mu, which is del mu prime basically. So del mu prime. Okay, now this is del over, I think I have done this before, so I could have skipped, or something similar I have done before, right? That's what I have done by using the chain rule, and there is a summation over nu. Okay, and this piece you can read from here. So del x nu over del x prime mu will give you e to the alpha, see from here, it will give you e to the minus alpha, okay, times the Kronecker delta. Okay, so this will give you e to the minus alpha del mu. Okay, so that one we can substitute. So because you have two such factors, each of them brings out e to the minus alpha, e to the alpha, because I am writing del mu in terms of del mu prime. So I get e to the 2 alpha, these are coming from derivative pieces, so del mu's, okay, and then this was coming from phi tilde, and this is anyway coming from the Jacobian. So you get half del mu prime phi x prime del mu prime phi x prime. Okay, so this together with these is your original action. If I rename prime to unprime, okay, so that's your S of phi. But then you have these additional pieces, okay, and you see that if d1 is 1, if d1 is equal to 1, then these two together form e to the 4 alpha, and this one is e to the minus 4 alpha, and you get the same action back. So if d1 is 1, actually you have to take d1 to be 1. Okay, so if you choose this representation, then your S of phi tilde is same as S of phi. Okay, meaning phi goes to phi tilde e to the alpha phi e to the alpha x. This transformation is a symmetry of massless Klein-Gordon theory. Okay, so that's one example I wanted to give. Now check that if you put mass term in this action, okay, check that m square, the mass term spoils the scaling symmetry. Okay, that gets spoiled because there is a mass, and mass is a scale. Okay, so if there is an explicit mass sitting in the problem, the theory will not be scale invariant, and that's why this will spoil the symmetry, okay, that we have found. So just do this. This is a fairly minor exercise because all other steps we have anyway done. Also check the following, that if you have the following massless theory, again real fields. But you don't have mass term, because as I said, mass will spoil the scaling symmetry. But if you take this Lagrangian, this section, this will still be scale invariant, and that's easy to check. I think we can check it right now. So this one anyway we have done, but let's look at this. This one 5, 4, and remember each here. So there is no derivative term now, because there is no derivatives here. So the derivatives are not going to bring in any such piece, but your phi tilde, instead of 2 phi's as you had in the kinetic term, you have 4. So you get e to the 4 alpha d1, where d1 is 1. So you get e to the 4 alpha, and that will cancel against this piece. So you see that this one will be invariant under scaling transformations. Okay, so that's one example I wanted to give, and we will continue the discussion on symmetries in the next video.